This is lecture 2 of Mathematics for Architects. In this lesson we're going to finish our introduction. We'll talk about intervals of real numbers, Cartesian coordinates, functions and segment notation. Again, hopefully the material in today's lesson will be mostly familiar to you. First, intervals of real numbers. A subset of the real numbers is called an interval if it satisfies these two rules. Rule number 1, we need it to contain at least two numbers. And rule number 2, the set must not have any holes in it. For example, the set of numbers x such that, remember this vertical line means such that x is a real number and x is strictly greater than 6. I've tried to draw a picture of this interval. It starts at 6 and it goes all of the way to infinity. This is an interval because there's at least two numbers in the set and there aren't any holes inside it. Before I go on, note that the number 6 is not in the set because 6 is not greater than 6. To show that the ending, 6, is not in the set, we use an open circle at 6. The set of all real numbers x such that x is between -2 and 5 is an interval. Again, I tried to draw a picture. Because the endpoints, -2 and 5, are in this set, I've drawn a filled-in circle at -2 and at 5. The set of numbers x, such that x is a real number and x is not equal to 0, is not an interval. It's not an interval because we have a hole inside the set. We can classify a finite interval as closed, half open, or open. It's closed if it contains both its endpoints. It's half open if it contains one of its endpoints but not the other one. And it's open if it does not contain its endpoints. Some examples. First, the interval where x is strictly between a and b. We have notation for this. We use round bracket a comma b round bracket. This is an open interval because the endpoints a and b are not in the set. We could have the numbers x such that x is between a and b. Now a and b are in the set, so this is a closed interval. For a closed interval, we use square brackets. Square bracket a comma b square bracket. Or we might have sets where one of the endpoints is in and one of the endpoints is not in. These are half open intervals. For example, square bracket a comma b round bracket. A is in the set, b is not in the set. Or round bracket a comma b square bracket. B is in the set, but a is not in the set. An infinite interval can be closed or open. It's closed if it contains a finite endpoint, and it's open if it's not closed. There's one exception to this rule. The whole real line R, we say, is both open and closed. Why do we do this? So that more advanced mathematics makes sense. When we do more advanced mathematics, we need to be able to say that the whole real line is both open and closed. Some examples. For example, round bracket a comma infinity round bracket. That's the set of all numbers x such that x is strictly greater than a. Because a is not in the set, this is an open interval. Or square bracket a comma b round bracket. Now a is in this set, so this is a closed interval. We could have an infinite interval which goes to -infinity in the same way. Or we could look at the whole real line. That's the interval between -infinity and infinity. The whole real line we say is both open and closed. We can combine two or more intervals with the union notation, which I introduced yesterday. For example, square bracket minus 8 minus 2, square bracket, union, square bracket 2 comma 8, looks like this. It's the set which goes all of the way from minus 8 to minus 2, and then we have a hole in the middle, and then the set which goes from all the way to 2 to 8. This set is a union of two intervals. It's not an interval itself because it has a hole in the middle. We'll need intervals later in the course. Something else we'll need is the idea of Cartesian coordinates. We can describe the position of points in a two-dimensional plane using two numbers. First of all, this horizontal blue line is called the x-axis. The vertical red line is called the y-axis. And the point where these two lines cross is called the origin. Let's say we have this green point, P. We can say that the coordinates of this point are 4, 3. What that means is if we start at the origin, first number is 4, we go to the right 4, and then we use the second number, we go up 3 to get to this point. Or, let's suppose we want to get to Q. Start at the origin, we go left 2, and then up 4. Because we're going left, we say that this is minus. So minus 2, and then 4. The set of all points in the plane, that's all of the points x, y, where x is a real number and y is a real number. We have a real number and then another real number. We have two real numbers. To describe this, we call this set R squared. Each one of these numbers is a real number, and because we have two of them, we write a 2 here. As I said previously, the point 0, 0 is called the origin. Let's suppose A and B are points in R squared, and A has coordinates 2, minus 1, and B has coordinates 3, 1. Draw the triangle OAB. In other words, draw the triangle which has coordinates at the origin, at A, and at B. The origin, we can draw the point 2, minus 1, 2 to the right, and then down 1 to get to the point A. The point B is 3 to the right, and then up 1. Straightforward to draw the triangle with corners at these 3 points. Draw the region of points which satisfy x's between 1 and 3. First thing I'm going to do is I'm going to ignore the 3, and I'm just going to look on the left side. I'm looking at x equal to 1. All of the points where the x coordinate is equal to 1. Could be the point 1, 0, the point 1, 1, the point 1, 2, the point 1, minus 1, etc. All of the points on this vertical line have x coordinate equal to 1. And then I might look at the right-hand side. I might look at x equal to 3. All of the points where x is equal to 3 is a vertical line. All these points which have x coordinate equal to 3. We are asked to draw all of the points where x is between 1 and 3. In other words, all of the points which are between these two lines. So we have this vertical strip. Draw the region of points which satisfy x is between 1 and 2, y is between 1 and 3. X equal to 1 is a vertical line like this. x equal to 2 is another vertical line of all the coordinates x equal to 2. Y equal to 1, all of the points where the y coordinate is equal to 1 is a horizontal line, and y equal to 3 is another horizontal line. We want all of the points which are between these four lines. In other words, we want this blue rectangle. We can measure the distance between 2 points. The distance between P1 and P2 we write as double vertical line, P1, P2, double vertical line. And we can calculate this using Pythagoras. The base of this triangle is absolute value of x2 minus x1. The height of the triangle is the absolute value of y2 minus y1. So by Pythagoras, the distance squared must be the base squared plus the height squared. Or in other words, the distance between P1 and P2 must be the square root of x2 minus x1 squared plus y2 minus y1 squared. For example, let's suppose I want to calculate the distance between 1, 3 and 4, minus 1. Put these numbers into the formula. First I'm going to use the first numbers, 4 and 1, 4 minus 1. And then I'm going to use the second numbers, that's the 3 and the minus 1, to get minus 1 minus 3. We're doing the square root of 3 squared plus minus 4 squared, which is the square root of 25, or 5. And that's all to say about Cartesian coordinates for now. Later, when we start thinking in 3 dimensions, we'll come back to Cartesian coordinates. The biggest topic for today is the topic of functions. If I write y is equal to f of x, I'm going to pronounce this as written at the bottom. Y is equal to f of x. Here, f is the function, x is the independent variable, and y is the dependent variable. What is a function? Formally, a function from a set D to a set Y is a rule which assigns a unique element of Y to each element of D. The set D of all the possible values of x, that's all the numbers we're putting into the function, is called the domain of f. The set Y is called the target of f. The set of all possible values of f of x is called the range of f. If we have a function with domain D and target y, we can write it like this. F colon D arrow y. So the function goes from D to y. 2 examples. The function which goes from the real numbers to the real numbers and has the formula f of x equal to x squared. Or a different function, the function f which goes from the open interval from minus infinity to infinity. But of course that's just the real numbers, that's the same. But now maps to the non-negative real numbers, which is the closed interval from 0 to infinity, and has the formula f of x is equal to x squared. Because these functions have different targets, that we can say that they're different functions. We might think of a function like this. We start at a set D and we're going to finish in a set Y. Point x in D is going to map to some point f of x. A point T might map to f of t, and a point P can map to f of p. If we counted up all of the possible points we're mapping onto, this is called the range of f, which is a subset of the target y. Another way to think of a function is some sort of machine where we put a number in and we get a different number out. We put a number x in the domain in, and we're given a number f of x in the target y. Let's look at some domains and ranges of some functions. First of all, the function f of x, which has domain from minus infinity to infinity. What possible values could y take? If y is equal to x squared, then y must always be a non-negative number. Y can be any number between 0 and infinity. It's not possible for y to be a negative number. Next line. Let's look at y is equal to 1 over x, where x is a real number and x is not equal to 0. What possible numbers y could we make? Think about this. If we have, let's say, x is 1, then we get y is 1 divided by 1, or 1. So 1 must be in the range. If we have, let's say, x is 2, then y is equal to a half. So a half must be in the range. What about if I had x is equal to, let's say, a quarter? Then y is equal to 1 divided by a quarter, or 4. 4 must be in the range. What about negative numbers? Let's say I had x is equal to minus a fifth, let's say. Then y is 1 divided by minus a fifth, or minus 5. Minus 5 must be in the range. If we think about this, every number apart from 0 must be in the range. It's possible to make every number y apart from 0. And I guess really I should have used the notation y just here. Square root of x. If x is any number between 0 and minus infinity, then y must also be between 0 and infinity. What about if x is the square root of 4 minus x? What values of x could we use? We could use x between minus infinity and 4. We couldn't have x is 5, say, because then we would have square root of minus 1, and that's not a real number. What values of y could we have? Let's take the end. If we take 4, say, we get square root of 4 minus 4, or square root of 0, which is 0. What about if, say, we take the other end? What if, say, we take minus infinity? Then it's 4 minus minus infinity, or 4 plus infinity, infinity. Square root of infinity is infinity. We could have all of the numbers between 0 and infinity. Y is the square root of 1 minus x squared. X must be between minus 1 and 1. If x is 2, say, then we're doing the square root of a negative number, which we don't want to do. What possible values could there be of y? Well, let's look at x is, let's say, minus 1, 0, and 1. If x is minus 1, y is the square root of 1 minus 1, or the square root of 0, which is 0. If x is 0, we're doing square root of 1 minus 0, which is 1. If x is 1, again, y is 0. Looks like y is going to be the numbers between 0 and 1, and that's true. 3 more functions. Y is equal to x squared, but with different domains. If x is between 1 and 2, then x squared must be between 1 and 4. If x is between 2 and infinity, then y must be between 4 and infinity. If x is between minus infinity and minus 2, minus 2 squared is 4, and minus infinity squared is infinity. Again, y must be between 4 and infinity. And the final two, y is 1 plus x squared, for x between 1 and 3. If x is 1, we get 1 plus 1 squared, which is 2. If x is 3, we get 1 plus 9, or 10. So y is equal to 1 minus the square root of x. We can have any number between minus infinity and 1. The graph of f, strictly speaking, is the set containing all of the points x, y, which satisfy y is equal to f of x. For example, let's suppose we're asked to graph or draw the graph of the function y is equal to 1 plus x squared over the interval from minus 2 to 2. Step 1 would be to make a table of xy points, which satisfy the equation. We're going from minus 2 to 2. So I'm going to use the numbers minus 2, minus 1, 0, 1, and just to check the shape, I'm also going to do 3 over 2 as well as 2. If x is minus 2, y is 1 plus 4, or 5. If x is minus 1, y must be 2. If x is 0, y must be 1, and so on. If x is 3 over 2, then y must be 13 over 14, or 3 and a quarter. Step 2 is to plot these points on the xy plane. And then step 3 is to draw a curve through these points. This is the graph of the function that we were asked to draw. Not every curve you draw is a graph of a function. To understand this, we have a test called the vertical line test. If we have a function, for example, 1 plus x squared on the left, then a vertical line should intersect the graph at most one point. This is because for each x value, we have one y value. As soon as we know x, we can use the formula to calculate the one value of y. However, if I drew a circle, some vertical lines would intersect the circle at 2 points. This tells us that a circle cannot be the graph of a function. If a is in the domain of the function, then the vertical line x is equal to a will intersect the graph of the function f only at the point a, f of a. I'm moving through lots of topics quickly. Next topic to talk about quickly is piecewise defined functions. We can use a different formula to define a function on different parts of its domain. For example, the function absolute value of x, we can use the formula this is equal to x is greater than or equal to 0, and we can use the formula minus x if x is less than 0. The graph looks like this. Or I could define a function f of x to be minus x if x is less than 0. That's the green part of the graph. I could define f of x is equal to x squared if x is between 0 and 1, the red part of the graph, and then I could say the function is equal to 1 if of x is strictly greater than 1. That's the orange part of the graph. Increasing and decreasing functions. Let I be an interval and let f be a function defined on the interval I. We say that f is increasing on this interval if we always have that f of x1 is strictly less than f of x2. For all points in the interval, we satisfy that x1 is less than x2. And we said f is decreasing. We have almost the same thing, except we change less than to greater than. Still, we're looking at points where x1 is less than x2. Some pictures. This is an increasing function because it's always going upwards. This function is always going downwards as we go from left to right. This is a decreasing function. This function goes up, down, up, down, up, down, up, down, etc. It's not increasing because it's not always going up. It's not decreasing because it's not always going down. We can classify functions, some functions, even functions, and some functions as odd functions. Let me quickly remind you, the numbers 2, 4, 6, 8, 10 are even functions, even numbers. And the numbers 1, 3, 5, 7, and 9 are odd numbers. For functions, these are the rules. Function is called an even function if we always have f of minus x is equal to f of x. And a function is an odd function if we always have the rule that f of minus x is equal to minus f of x. Let's look at some examples. I am saying that the function x squared is an even function. Why is this true? Because if we start at f of minus x, that's minus x squared, which is the same as x squared, which is the same as f of x. Because we always have f of minus x equal f of x, this is an even function. In terms of graphs, even function is a function where the left side of the graph is a mirror image from the right side of the graph. I'm saying that x cubed is an odd function. Why is this true? Because if we start with f of minus x, or minus x cubed, we can see this is the same as minus f of x. terms of graphs, an odd function is a graph where if we take the graph and we rotate it 180 degrees about the origin, then we have the same graph that we started with. For example, is f of x equals x squared plus 1 even, odd, or neither? You have some homework questions like this. What I do is I start with f of minus x. Then I calculate that's minus x squared plus 1, or x squared plus 1, or f of x. Because f of minus x is always the same as f of x, we have an even function. If we want to show that something is even or odd, we need to show that the rule is true for all x. Next example is x plus 1 even, odd, or neither. This time I'm not going to use every x, I'm just going to choose one number. Note that g of minus 2 is minus 1, and g of 2 is equal to 3. So g of minus 2 is not the same as g of 2. We don't have an even function. G of minus 2 is not the same as minus g of 2. So we don't have an odd function. Therefore, this function is not even and not odd. If we want to prove that a function is even or is odd, we need to prove that the rule is true for all x. If we want to prove that a function is not even or not odd, we only need to find one number where the rule doesn't apply. We still have quite a bit to do. I'm going to take a 5-minute break. And let's continue. I'm going to briefly go through some different types of common functions. First, linear functions. These are the functions where the graphs are straight lines. The formula is of the form mx plus b, where m and b are numbers. For example, the green line is a half x plus 1, the orange line is minus 3 over 2, etc. The power functions are f of x equal to x to the power a, where a is a real number. For example, if a is 1, we have a linear function. If a is 2, we have y is equal to x squared. We have y is equal to x cubed, y is equal to x to the power 4, etc. We could also look at negative numbers, because x to the power minus 1 means 1 divided by x. Or we might have 1 over x squared, or x to the power minus 2, etc. We could allow fractions, for example, if a is a half, because x to the power of a half means square root of x. We might have a as a third, x is 3 over 2, x is 2 over 3, etc. If we have a number multiplied by a power function plus a number multiplied by a power function, etc., this is called a polynomial. The domain of a polynomial, by which I mean the biggest possible domain, is always the whole real line. We might do polynomial divided by polynomial. This is called a rational function. For example, 2x cubed minus 3 divided by 7x plus 4. 2x cubed minus 3 is a polynomial. 7x plus 4 is a polynomial. Polynomial divided by polynomial is called a rational function. A to the power x, where a is a real number, a is greater than 0 and a is not equal to 1, is called an exponential function. I've drawn the graphs of some exponential functions like this. The inverse of an exponential function is a logarithmic function. I've drawn the graph of some logarithmic functions. Now, if I go back to the previous slide, the exponential functions look like this. Let's suppose we put a mirror along the line y is equal to x. Just imagine there's a mirror here. Think about what would be the reflection of these graphs. The answer is we would have these graphs, because a logarithmic function is an inverse of an exponential function. Before I finish this chapter, I want to talk about angles. Two common ways to measure angles. We could use degrees or we could use radians. I want to discuss radians briefly. What is a radian? Imagine that we have a circle of radius 1 and we measured around the outside of the circle. This distance is the angle in radians. For example, look at the picture on the right. Suppose we have a semicircle of radius 1. We know that the angle in the middle is 180 degrees, And we know that the distance around the outside is half the distance around a circle, half the circumference of a circle, so this must be pi. So 180 degrees is the same as pi radians. Divide both sides by pi. You can say that 1 radian is the same as 180 divided by pi degrees, or 1 degree is equal to pi over 180 radians. 3 common angles. 45 degrees is the same as pi over 4. 60 degrees is the same as pi over 3 radians, and 90 degrees is the same as pi over 2 radians. When we use degrees, we have to use this little circle, so we know we're using degrees. If we use radians, we don't need to use any symbols. Anytime in this course you see an angle with no little circle, it will always be radians. In calculus, we have to use radians. When we get to part 4 of this course, all of the angles will be in radians. Why? Because calculus doesn't work if we use degrees. The final types of functions to talk about are the trigonometric functions: sine, cosine, tangent, secant, and cotangent. What does sine mean? Imagine we have a circle and we have a point on the circle. We can measure an angle, we can measure the coordinates of the point in x and y coordinates. And we have our circle of radius r. Sine of theta means y divided by r, and cos of theta means x divided by r. Once we have these, we can define the other 4. Tan means sine divided by cos. Secant means 1 divided by cos. Cosecant, which can be written in 2 different ways: cosec or CSC. In this course, I'm going to be using cosec because I think it makes more sense. This means 1 divided by sine, and cotan means 1 divided by tan. Just to be careful here, tan and sec are only defined as long as cos is not equal to 0, and cosec and cotan are only defined as long as sine is not 0. We calculate sine, cos, tan, sec, cosec, and cotan of 45 degrees, or of pi over 4, using this triangle. Base 1, height 1, 90 degrees, or pi over 2 angle just here. By Pythagoras, the other side must be the square root of 2. Sine means the height divided by the hypotenuse, 1 divided by root 2. Cos means the base, 1 divided by root 2. And as soon as we know sine and cos, we can calculate tan, sec, cosec, and cotan using the formulas on the previous slide. We can also do 60 degrees, or pi over 3. I'm starting with a triangle, equilateral triangle of sides 2, and I'm going to cut this in half. Imagine cutting this triangle in half. Then we have the angles pi over 2, pi over 3, and pi over 6. Base 1, hypotenuse 2, and by Pythagoras, the other side must be root 3. I will leave these sine, cosine, etc. for you to check. Graphs of sine and cosine look like this. The functions go up and down, up and down, up and down, etc. The final chapter for today's lesson is chapter 7, sigma notation. Let's suppose we want to add lots of numbers together. instead of writing a1 plus a2 plus a3 plus a4 plus etc., we have a nice, neat way to write this. We could write it like this. What does this mean? This large symbol is a Greek letter, capital sigma. The k equal to 1 on the bottom means that we start at 1. The first one is a1. And the n on the top means we finish when we get to n. The last one in the sum is an. For example, if I want to do 1 squared plus 2 squared plus 3 squared plus 4 squared, etc., all of the way up to plus 11 squared, I can write this as sigma k squared, because all of these terms are a number squared. We start at 1 and we finish at 11. Or if I want to do f of 1 plus f of 2 plus f of 3, etc., I could write this as capital sigma f of k, start at 1, finish at 100. Calculate the sum from 1 to 5 of k. We start with 1, and then we do 2, and then 3, and then 4, and then when we get to 5, we finish. We get 15. The sum from k is equal to 1 to 3 of minus 1 to the power k, k. First we do k equal to 1, so you get minus 1, 1. And then we do k equal to 2, so minus 1 squared, 2. And then we do k equal to 3, minus 1 cubed, 3. And then we stop, because the number on the top is 3. And it turns out that this is equal to minus 2. The sum from k equal to 1 to 2 of k over k plus 1, I'll leave for you to check, is 7 divided by 6. We don't have to start with k equal to 1. We can start with any number that we wanted to. For example, we might start k equal to 4. First we use the number 4, and then we use the number 5, and then we stop. You can check that this is 139 divided by 12. I want to find a formula for 1 plus 2 plus 3 plus 4 plus 5 plus 6, etc. up to plus n. And what I'm going to do is, instead of calculating, I'm going to calculate a formula for double this, for 2 times 1 plus 2 plus 3 plus 4, etc. And the way I'm going to do this is I'm going to write first 1 plus 2 plus 3 plus 4 plus 5 plus etc. up to plus n. And then I'm going to do the same thing in reverse. Starting at the biggest number, plus n, and then the next biggest number, plus n minus 1, plus n minus 2, plus n minus 3, plus n minus 1, etc. And finishing at plus 2 plus 1. Why have I written it like this? Because, look at the first 2 numbers. 1 plus n, that's the same as n plus 1. And then I have 2 plus n minus 1. Well, that's just n plus 1. And then I have 3 plus n minus 2. Well, that's just n plus 1. All of these are n plus 1. So really we have n plus 1 plus n plus 1 plus n plus 1 plus n plus 1, etc. How many do we have? We have n of them, n times n plus 1. Then all I need to do is divide by 2. The formula that I'm looking for is n plus 1 divided by 2. 2 similar formulae, which are more difficult to prove. The sum of the first n square numbers is n plus 1, 2n plus 1 divided by 6. And the sum of the first n cubed numbers is n plus 1 over 2, all squared. And that is the end of today's lecture. That's the end of the introduction to this course. Next time we're going to start talking about geometry. We'll talk about polar coordinates. That's another way to describe the position of a point in the plane. We'll talk about conic sections, shapes which are often used in architecture, and we'll talk about three-dimensional Cartesian coordinates. Do you have any questions?